Hi, so I was thinking about this and I just realized I've never actually made a video about graphing of either logs or exponentials, which is actually a fairly significant concept for us. We go through it fairly quickly because we've already done a fair bit of graphing by transformation, but that doesn't mean that everybody really has all those skills down. So hopefully this would be helpful to you if you are in any way struggling or just looking for clarification on an issue. So let's take a look at a little bit of the mathematics behind this. So first off, when you're dealing with any kind of, in fact, hold on just a second, let me double check and make sure I'm sharing the thing that I meant to. I want to share a Desmos window with us. So let's take a look at the Desmos real quick. So keep in mind that anytime you graph an exponential, y equals 2 to the x, for example, we have this nice little upsloping curve with a horizontal asymptote at y equals 0. You see that red line. Now, as we change this from 2 to the x to 3 to the x, for example, I'm going to go ahead and just grab this one here, and let's just change this to the number 3. Now, you'll notice it has a lot of the same criteria. It still has that horizontal. You'll notice it also goes through 0, 1, because anything to the 0 power is 1. If we change that 3 to a 4 or a 5, or a 6, you're going to notice that those lines just become successively more and more and more steep, but they get flatter and flatter and flatter to the left side towards that x-axis. Of course, if we then made those numbers instead of larger, we made them smaller, like say maybe we made it 1.5, you'll notice it's a little flatter, or 1.1, even flatter. And that almost looks like a line, but it's certainly not. Maybe 1.2, you can see a little bit more curvature there. And then, of course, if we ended up making that value below the number 1, like say something like 0.8, the difference is now instead of growth, it becomes decay. It's actually going to the left. I think one of my favorite values would be is 0.5, because that's actually 1/2, which is really 2 to the minus 1, and you'll notice the reflectivity of that graph across the y-axis. But all of these graphs have that same story of having that horizontal asymptote at 1, and at its root, every single one has a y-intercept of +1, no matter what I do. So that's kind of what you would do if you had Desmos and you could play with it very quickly. But on a test, of course, we don't have that, and we want to be able to execute some problems relatively quickly. So I have a couple of problems set up that we're going to look at. The first one is right here. We're just going to take a look at y equals 3 to the x. Again, not a hard problem by any stretch of the imagination, and also e to the x. We're going to do two very simple ones, and then down at the bottom, we're going to have a couple that have some more difficulty associated with them. So pretty typically, people pick fairly small numbers in exponentials because according to what you saw to the left of a normal exponential, it goes down to the x-axis as an asymptote very, very, very rapidly. So it's hard to graph. Like if you plugged in something like -1, you got 1/3. Now, -2 would be nice too, but that's 1/9, and that is such a small number that it's almost indistinguishable from the horizontal asymptote. So having a fairly small negative number is nice, but honestly, you don't even want a very big positive number either, because if I plugged in 2, it'd be 9. I already have to have the graph fairly large to actually fit that. And of course, we already know that it has a horizontal at 0. So we have our horizontal at 0 going like this. We have our coordinate at -1, we're sitting at 1/3. At 0, we have 1. And at 1, we have 3. And we have nice, easy looking graph right here like this. Please remember to make them relatively generous in terms of their length so you can show the entire curve. Now, coming over here to e to the x, not everybody feels super comfortable with this because e is one of those transcendental numbers. It's an irrational value like pi that goes on forever without repeat. But we're going to label this thing as -1 gives me 1/e, 0 gives me 1, and 1 gives me e. Now, again, that's what the math says, but of course, a math student is like, well, where do I graph 1/e? Well, if you plug that into a calculator pretty quickly, what you would find out is that 1 divided by e, because e is right above the divided by sign right here, you end up with, whoops, 1 divided by e is 0.37-ish, okay? Now, of course, normally I like to go to 3 decimal places on everything, but the reality is the graph of 0.367 and 0.37, I can't tell the difference on a graph with this kind of accuracy level. And we should be aware that E itself is 2.718, okay? So about 2.7 would be sufficient to give us an idea where it is. So our value A, B, C, with of course our horizontal asymptote y equals 0 is going to give me this value right here. So at negative 1, I'm sitting at 1 over E, which is just about a third. B, of course, is right there at 0, 1 as always, and 1 gives me E, which is just a little teeny bit below the number 3. There's my value C. We can sketch our graph in like this, together with, don't forget your horizontal asymptote, y equals 0, and we have a nice looking graph. Okay, now let's go ahead and make that problem a little bit more difficult, okay? So, actually, yeah. Let's go ahead, and I did have this prepared to look at this problem in Desmos real quick, just to make sure that we were accurate and did a good job. So our question number 1, the first thing that we should always do is create a table with a couple of points, which I did right here. You'll notice you can actually click on those points and it'll actually show you that they are identified. We made sure I put my horizontal asymptote, and then I graphed this spot right between those values, and it looks pretty good. Like I did an okay job on that particular graph. So I'm going to turn all those things back off so they're not in the way. Number 2, my exponential story. Keep in mind that I had my horizontal asymptote at 0 as always, the values that we discussed. Again, if you click on them, you're going to see the decimal approximations that I showed you earlier. This is what Desmos automatically did. I didn't actually tell it to approximate that to 2.718. It just automatically will do that. And then, of course, a quick sketch of the graph. Not exactly surprising, not exactly difficult either, but just wanted to get the basics out of the way before we do a problem that's a little bit more robust. Okay, so now let's go to the harder problems, the ones that might actually cause you a little bit more concern. Now, on a test, I would be very, very, very likely to ask you a question like this one right here. Y equals 4 raised to the 2x plus 6 minus 5. Just there's a lot of stuff going on. And different teachers will have different approaches to this problem. But my estimation is that if I thought of f of x being my parent function, 4 to the x, I'm going to play that game just as we always have. And let's say we tried -1, 0, and 1, just as always. Now, we could have tried 2, but even 4 to the 2 is 16. It's pretty large. So I have a couple of very easy values as demonstrated earlier. That is my parent function, if you will. But now we want to figure out what is this new y that somebody created, because it is a modification of f itself. So if f is this guy right here, well, not much happened on the outside of this function. The only thing that happened on the outside is this -5 right there, which means I know that every y value has been slid down 5 numbers. So this y equals 0 has become y equals -5. So I'm going to go ahead and put that horizontal asymptote in down here. Y equals -5. I have the number 4 is going to become -1. The number 1 is going to become -4. And the number 1/4, if I slide down 5, also known as 20 quarters, 1 minus 20 quarters is -19 quarters. Not a really super nice number, but not terrible either. And then I have to look at the inside. And we have this special little thing that we keep saying, and this is bugging me that 5 as well. I looked away as I wrote it down, is that we never have anything attached directly to x. So every x value, I could pull out that 2 and then put a +3. So according to what we've been discussing in class, anything on the inside affects the x value and the x value only. And it does so in an opposite way. So this says, let's multiply by 2 and add 3. So what we're going to do is we're going to divide by 2 and subtract 3. So if we took -1 and we divided by 2, we get -0.5. And then if we subtract 3, we're going to get negative 3.5. If we took 0 and we divided by 2, we get 0. And then we subtract 3, or 1 divided by 2 is 0.5, subtract 3. So one thing that you might want to notice is originally in their problem, look at the separation. It was 1 unit here, 1 unit here. Here, the separation is just half a unit and a half a unit, and that's because the x value is contracted. There was a horizontal contraction in this graph, sliding it in ever so slightly. So now we can actually go ahead and graph that. We can go to negative 3.5, so here is A. So we're going to go to negative, and here's B and here's C. Let me go ahead and label those so I can put it on the graph. So I'm going to go to negative 3.5, and I'm going to go down to negative 19 quarters, which is just above negative 5. Let's go to negative 3 and negative 4. That's going to be sitting right here. Notice how tight this is. And then C is negative 2, let's see, 1, 2.5 right there. This feels like it's a little bit wrong. That is wrong. So I had negative 3.5. Oh, I had those wrong, didn't I? Let me fix that real quick. I didn't look at my graph carefully enough because it was negative 3.5. There's A. Negative 3, comma, negative 4. There's B. And negative 2.5. That feels better, comma, negative 1. Here is C, and then we have our graph cruising down here like this, getting super close to the axis. And that graph looks, I mean, it's always been steep, but this is even steeper than normal because of that horizontal contraction. It was already a steep curve, and we slid it into the side. So again, one thing that I'd like to see you do, and this is just something that I find to be very important in math, is just to check your logic and make sure that what you're doing works so that when you do a test or something, you have a higher level of confidence in the math that you're doing. So I started off by taking a look at those values that I had contracted. That's what I got. I also got that horizontal asymptote at negative 5, and then when I graphed it, I can see that the values that I did, the graph that I produced, is accurate, and I'm confident that my process worked. And it didn't take me very long, just took me a couple of minutes to do that. Now, of course, the last one is the one that I think most students would actually have probably the least level of confidence in, and that's when we start dealing with E. And there's a couple extra little nuggets in here that are problematic for people. So let's start with this idea that my parent function f of x is e to the x, which I already did above. That was negative 1, 0, 1. That was 1 over e, 1 and e. Again, I'm just copying those values that I had previously written on the top of my paper. In fact, I think I'm going to fold this thing over so that I don't have to keep sliding it on the camera quite so much. So let's say that's what we have. I covered up my paper just a little bit. That's all right. So what has happened when I look at this y? Well, the first thing I notice is that there was a 2 sitting on the outside. So there was twice f somehow. We also have a plus 1 that's sitting out here. Now, both of these values will affect specifically the y value of that thing. That is going to do exactly what it says. It's going to take the y value, it's going to double it and add 1. So if I took 1 over e and I double it, I get 2 over e and I add 1. If I took 1 and I double it, I get 2 and I add 1 and I get 3. If I take e and I double it, I get 2e and I add 1. Now again, not pretty numbers, but it's okay. This one is 1.74. This one is 6.44. So that just gives us a little bit of an estimated value as to about where those values should be. And of course, y equals 0 got multiplied by 2, still 0, and added 1. So we got 1. So I have a nice little horizontal asymptote at y equals 1. This one got shifted up a little bit. Now, let's go ahead and finish the harder part of that question. On the inside, I had not folded it quite like I had, but we had 1 minus 1/3 x inside that function. So again, we never let anything be attached directly to x. So if I factor out a 1/3, then if I factor out a negative 1/3, there's going to be an x left inside there. I'm going to put that over here. There's going to be a negative 1/3. That's going to be an x. And keep in mind, When you factor, you're dividing. So if I divide 1 by 1/3, you're going to get the number 3. And a negative times a negative would be a positive. And to check my logic, what happens if I distribute? Negative 1/3 times x is negative 1/3 x. Negative 1/3 times negative 3 would be positive 1. That's the number that's going in here. So we actually have a nice, let me go ahead and make that look a little bit prettier. So my y that I'm generating is f of negative 1/3 parentheses x minus 3 with a plus 1 at the end and a 2 at the beginning. So what we're going to do is we have a total of three transformations, actually 4 transformations. 2 were vertical and 2 were horizontal. Actually, 3 were horizontal. I'm going to flip it across the axis. That's going to make these numbers positive, 0, and negative. I'm going to multiply them all by 3. So negative 1 became positive 1. Then it got multiplied by 3 and it became positive 3. And then I'm going to move to the right 3 and it becomes positive 6. Now again, let's talk about that again. Negative 1 first flipped and it became positive. Instead of dividing it by 3, I multiplied it by 3. So that positive 1 became positive 3 and then I moved it over. 0 gets flipped, which makes it still 0. I triple that number, which makes it still 0. And then I move it to the right 3 and I got 3. And last, 1 gets flipped and becomes negative 1. It multiplies by 3, it becomes negative 3, and then it moves to the right 3, and I got 0. Now, again, like I did on the other one, keep in mind that the separation of these were just exactly 1 unit apart, and now they're 3 units apart because that horizontal stretch factor that is sitting right there means that the x values got tripled in this direction. And that makes sense with our value. So we have 6 over here, 3, 4, 5, 6 is going to give me 1.74, which is about right here. I'm going to call that one A. 3 gives me 3. We'll call that one B. And last but not least, 0 gives me 6.44. 1, 2, 3, 4, 5, 6.44 here, C. And we have a nice little graph coming in here about like that. Now you'll notice that this one is going down, and it's going down because we have that negative exponent that is sitting right in here. Now again, it doesn't totally look like a negative exponent, but if I open it up so you can see the whole thing, this e is being raised to a negative x power, which makes it exponential decay. So with that in mind, that would be a pretty hard problem. And so we are very likely to make some small mistakes in it. So it's always a good idea to double check. So let's go ahead and throw these data values into a table and make sure that my data values were in fact accurate. Let's put our horizontal asymptote in and see how it worked. So let's see. Back to Desmos, here we go. Number 4. I put in those values into my table. Oh boy, they don't fit very well, so I need to move this around just a little bit. I had that horizontal asymptote at 1 that we had listed previously, and then I typed in not just a question, but I typed it in literally the exact same format the test was given. The question was given just in case I made a mistake in factoring and whatnot, but I've got that thing right there. Now, one thing that we can do too is sometimes it's a good idea as you're playing with your graphs is to take something like this. Let's copy that and paste it down. I'm going to turn this one into a dotted line for a second. And let's just play with what we did. If we called this thing f of x, and I want to see what happened if I messed with it a little bit. So a second ago, we just said that, oh, let me fix this just a second. Okay, that's what I wanted to do. Let's say I made f of x equals e to the x, because that was our parent function that we decided we wanted to deal with. Now, we said that the 2 goes on the outside. Now watch what's going to happen to the green graph. It got taller. We said we put a plus 1 on the outside. That's going to slide it up a little bit. Now, right in here, we said we don't want anything to be attached directly to x, so we figured out we wanted to factor out a negative 1 third. That's going to flip that graph over. And then, of course, last but not least, we had a little transformation of a -3, which of course moves the graph to the right 3. And we'll see that those values that we produced were in fact step-by-step accurate. Okay. Hopefully that was helpful. I'll post a second video that has to do with graphing and analyzing logarithmic graphs. Okay. All right. I will see you back in class. Bye-bye.